Hello, Pradeep. I'm audible.
Yes, sir, you're audible.
Okay, okay, thank you.
Yeah.
Okay, let us wait 5 minutes, then we'll
Let's start.
start.
Yes,
Yes.
yes.
Okay. Pradeep, in the meantime, you can read this PPT, right? You will
Right, sir.
get some, yeah, you will get
Yes,
some
yes.
information regarding that.
Sure. Thank you, sir.
Yes. Let us wait more 2 and 3 minutes, then we'll start. In between, Francis, if you want, you can tell. You can read actually, whatever you are. How I'm audible?
Yes, sir. Yep.
Yes, sir.
Oh, okay, okay, okay. Francis, you read the whatever the written in the PPT. You will get some information why we use the circular pipe as the place of rectangular.
So actually, I have a doubt relating to the last class. Can I ask it now?
Yes, yes, sure.
While selecting the repeating variables, do we need to consider that both the M, L, and T need to be in that, or the variables that we select, three variables that we select, should contain at least one variable? I mean, if the repeating variables are M, L, T, then if we select three variables, then one variable contain length, one variable, the other variable should contain length and time. I mean, if we take the three variable, it should contain three repeating variables. Is it like that?
No, no. What was in the previous class I was telling for the as per the Buckingham Pi rule. Actually, these are the rule. Uh, well, Actually, the repeating the Buckingham Pi theorem was about the repeating variable kind of thing. So we, as per the rule, we need to select the three variable which is having the primary, the fundamental dimensions. The reason behind it, uh, basically in the all whatever you have derived the pi 1, pi 2 and pi 3, these all the variable should be there in the pi 1, pi 2, pi 3, and it will be when you merge the all pi variable and make the dimensionless the final pi, then it will be more utilized and more actually applicable kind of thing you will get. So that is the reason we select the three fundamentals different family. Let's know mass and the length and the time parameters.
In that case, if we take three variables and if we collectively take three variables, it should contain the both these three variables. I mean, maybe one variable will only contain L, but the other in the other two variables there can be M or L.
No, no, no. M or T should be also there. If let's if variable is not there, let's say for the previous class one we have solved the one example, only we have selected the two variables because of the as per the question framed like that. As per the question, we have selected the two variables. In that question, we have select what I think W. We have taken the W as a repeating variable and the Z. I think the depth of the these two things we will take the variable as a repeating variable. So so this is the because in the W the time things is already in there, and actually W was a known parameter. So because lots one table I was provided in the previous class, so that table will also help the which type of you need to select the variable during the Buckingham Pi term. So Francis, I will suggest you go through once the table, then your doubt will be definitely clear. Whatever you are asking definitely will be clear.
Okay, sir.
Yes. So now I think let us start. I think no one. Okay.
So the omega is taken as a fluid property or fluid property omega.
Omega means what?
I, the
Rotation?
angular velocity, rotation angular velocity, is it the fluid property or flow property?
No, it is a flow property. Fluid
Flow
pro.
property.
Yes, this is a flow. This is a flow property, not fluid.
Okay, sir.
Yes. So I think now we'll start because I think it's already 8:10, 18:10. So welcome in the week 8 fluid mechanics live TA session. So today week 8 is about the incompressible viscous flow in the pipe. Viscous flow is very important, and this is the very basic beginning of the fluid mechanics. I think my pen is not working. Just wait. Viscous flow, really, it is in everywhere. If you are the fluid mechanics engineer or civil engineer or mechanical engineer, whatever, this topic is very extensively used in your research as well as everywhere. If you go for any interview, then from this chapter, people definitely ask the question, lots of questions. So in this chapter, we'll study about the laminar and the turbulent flow, how the flow is, what happen if the flow will be like that, the laminar, and what will happen if the flow is like that. So this type of study will see in this and the loss in the pipe fittings and the flow in non-circular conduit and the multiple path pipe flow. That is the multiple path pipe flow means that is a single pipe, and from the single pipe lots of pipe is connected, 2 3 pipe is connected, and again it's meet in the single pipe. So this kind of thing we will study. Or so basically one question in the mind before we are going to on the question, we will some see the concepts behind it or the flow. Actually, water flow, or maybe you can say the fluid flow. So why basically you generally you will see the we will use the circular pipe at the place of the rectangular duct. Duct or pipe is both are we will use in this class the pipe and duct is a similar thing. So you have probably noticed what the most of the liquid flow in the circular kind of thing, not in the rectangular. The reason behind it, the I have written some reason here. The efficient flow, that is the minimize the friction losses. How minimize the friction losses? Less energy required to move. Let us the circular pipe offer the most efficient flow of fluid compared to the other shape. The circular cross section minimize the friction losses because at the corner point there are friction losses is the more as compared to the smooth one. So this is the reason. So that is the reason we use the circular, and the one is the uniform distribution of the pressure. At the corner, uniform pressure will not distribute, but in the circular case, the pressure will be uniform distributed everywhere. That is on each and every point of the perimeter. But in case of the rectangular one and other shape, this is not. So this one is again the important reason for why we use, and the structural integrity, and also the stress distribution is uniform. So that is the reason behind it. This is the three point I have taken the more point also. You can take the screenshot why the manufacturing is here and the versatile maintenance resistance to corrosion and the description was given there. So, but these three, the technical reason why we use the circular pipe at the place of uh, rectangular one, why we are not using the rectangular one. So, as we have seen the already in the many classes I have discussed how the velocity variation in the pipe in case of the laminar flow. Here we will see also the turbulent flow case as already here drawn. So basically the maximum you see here the distribution is like that. At the wall velocity is 0 due to the no slip condition at the both wall. You can this is the pipe. You can so at the both end the velocity is 0 and increasing towards the mid of the pipe. At the mid the velocity is maximum. So this is the very basic thing. So these are the some derivation. There is no meaning. But in case of turbulent, how we will see the turbulent flow look like? How look like the turbulent flow? Here the figure is given. The laminar flow only the straight thing is there. But in case of the turbulent flow, the flow is like that. You can see here the zigzag pattern of the flow. In between transient also come. So we will see the transient thing also. Is it visible or not? Yeah. The slide is moving properly.
It was moving. Now it
Okay, okay.
we're at the turbulent flow.
Yes, yes. So I think this is the very basic things. I will not take much time. So how turbulent and the laminar flow is going. These are some basic. Now again, the Reynolds number you know already. Based on the Reynolds number, one experiment was done by the Osborne Reynolds in 1980s. So basically, the Reynolds number is the ratio of the inertia force divided by the viscous force. And inertia force we will write the inertia force here is written inertia force means the force due to the mass rho mass flow rho average velocity average into L square. So this is the force inertia force divided by viscous force is due to the viscosity of the viscous force is this length. So based on this ratio, we will define actually whether the laminar flow or whether the turbulent flow, and in between we consider the transient flow. So this is the very basic kind of thing. So the ratio when you calculate when you the final ratio is this rho velocity average, that is the average velocity. In the previous slides you might have seen the average velocity like this. This is we consider the average velocity, not the maximum. So this is the basically the definition. So now coming on the next, these are the basically in D here. What is represented D? You will see the D is the uh, hydraulic diameter. So hydraulic diameter we will generally for circular pipe it is D, but for non-circular pipe how will we calculate the DH, that is the hydraulic diameter is given as DH barabar 4AC divided by P, and the 4AC means what? This is the area actually, cross section area. For circular case if we calculate, 4 AC divided by perimeter, how it will come? 4 AC is equal to what? Pi by 4 into d square for circular case divided by perimeter is how much? Pi d. So this is gone off. 4 is 4 more and d square. Only d is remaining. So in the circular case, the dh is equal to d. Similarly for rectangular, you have seen here what is the rectangular case and the channel if they are given, and a square duct if is given, it will be the side of the square duct. So similar this based on this we will calculate the Reynolds number for the different shape of the duct. So here the Reynolds number range is given. This is the experimental data. On the basis of experimental, it is defined as the Reynolds number is less than and equal to the 2 3 here. 2 3 somewhere I have seen the 2000 is also given. So there is not much worry about it. So if the Reynolds number is greater than and less than and equal to 2300, the laminar flow is there, and the in between the transient, and if the Reynolds number is greater than 4000, it will be the turbulent flow. So this is the very basic thing. But this was, I think, for you, for some, not all of you. This was the new thing. The hydraulic parameter was the dH is equal to 4AC by perimeter. So now this is a very interesting thing. Always people was asking whenever you will go for some interview, what is the development line? Let's say the pipe is there and the water is flowing from here. So when the water is flowing with this velocity, you have the average velocity. Water is flowing with the average velocity. What will? So the velocity diagram is like that, not the parabolic one. After the certain distance, the velocity will be the parabolic. That is the from this distance is known as the hydrodynamic entrance region or fully development length also. For the Reynolds number, for the laminar case, this development length, let's say the LD is 0.7 RE, that is a Reynolds number, into the diameter of the pipe for laminar case. For turbulent case, lots of experiment was there suggesting the 40 to I think 50 of diameter, or someone reported the 30 to 40 times of the diameter of the pipe for the turbulent case. So there are several research was there about the development length. So this is the very basic thing. What is the development length? I think you have got.
So this LD is actually the fully developed length. I mean the length.
LD, yes, yes. The distance from the entrance, whatever the, let's say this is the pipe inlet. If your water is entering from here, water, or let's say the another thing, if the entering from here, up after how much distance, your velocity diagram will be look like the like this, the fully parabolic. After that, there is no change of the velocity diagram. Similar, if the pipe was extended, the similar, there is no change in the velocity diagram. Similarly, this similar here, the diagram will be the similar. But if you see here, the diagram, velocity diagram is different, this one different, this one different. So velocity that is your velocity developing, but after that there is no change in the velocity diagram. So that's why up to that much distance we known as the development length or the velocity development length in the pipe. In the pipe case, this formula is valid, not everywhere. In the open channel, you cannot use this thing. In the open channel, I have seen in the several researcher reported as the in the open channel this development length is a 42, not 55 to 65 of flow depth. Let's see the Y in the open channel case these things and the turbulent flow. So this is very very important. 0.7 0.07 RD, and this was, I think, you need to be remember every time. So this is the very basic
For the
definition.
open channel, how it will be the fully development flow means. I mean,
Yes,
for the
yes.
pipe it will
Okay,
be
okay. For open channel case, let's say from top you, this is the open channel. From top you are seeing, right? Let's say the river you are looking from top, but from side view, this is the side view, and depth is a y. This is the bed of the channel. So I think you remember the boundary layer theory like that. But after certain distance, it will be the uniform. So up to that, this is the development length LD, and this people, several researchers reported that it will be the range of 55 to 65 times of y. So if you are going to some measure the data like velocity, if you want to measure, you need to measure after that, after this development length, not in between the, not inside the development length, because your velocity variation is going on. So you, after development length, you will take your data, the velocity, how much the velocity in the pipe. On that basis, you will design your pipe, and in the open channel case, you will design the another structure or kind of thing. So this is the reason behind it. We study the development length. So
so
naming
in
is
the top view, is there
yes.
any profile when we view from the top? Is there any profile for this flow open channel?
No, no, no. Just for you, I have shown the top for saying the maybe. But actually, the in case of river, if you will see, the river is very wide. So generally, here also in the wall boundary layer will be developed, and from bottom also will be the developed boundary layer. But very wide channel, so we is generally focus on the bottom kind of thing, not on the wall. So some naming is there, the irrotational flow or the core flow region. This is the whatever inside this. These are the core flow region. So you always remember what is the core flow region. After that, you will see here. This is the boundary layer kind of thing. If you look like this is the boundary layer. This is a pipe. If this is the boundary layer, after certain distance, the boundary layer is remain. There is no change. So similarly, will happen in the open channel case or everywhere. So now we'll move on the next. So basically, that was the length of the what I was telling. This is only in this case here the 0. What I was telling, the 0.07 RE D here is what given 0.05, approximate 0.05 RE into T. So in some book 0.07 written, in some book this written. So but if you going to solve any problem, I think it will be the range of when you will solve the both, you will be get definitely certain. Uh, you got the your answer in the range, not exact answer was given like that. So you must remember like, and who is giving, some researcher is giving this, but this actual data is given by these researchers in 2004, and Sa and Bhati in 2000, 1987. So for
So
turbulent
this
case,
entry length and the, both are different in entry length and that. we calculated that LD before, isn't it, for pipe?
No, LD or LH here same, but in this book, I think it is represented by LH. You are talking like that. This for LD or LH is same.
Yes, sir. Yes, sir.
Yes.
So we can use the both formula.
Yes, yes. When you will use some researcher when the performing the research on pi, they get like that, and some researcher if these four researcher is doing the research, what we get the 0.05 RDX. So when you solve the this formula, you made your if answer is given, let's say the A, B, C, D, whatever your answer is given in the question. So if you are getting by this, you take. But if you are not getting by this formula any option, then you can go on the another formula also. So for turbulent case also some researcher is giving. For turbulent case this is, and generalize you can the for the development length for the turbulent case 10 times of the D. So this is the development length concept. How you will get? Why we are looking at development? Because of the when we measure the velocity in the pipe, we look after only the development length, not before the development. So now we'll solve some questions, very easy questions. So I think first and second question you might have seen. I think some another. No, I don't have the another concept. So please, for question one and two, you need to solve and write your answer in the chat box. The first question is about the friction factor of laminar liquid flow. Actually, liquid flow in a circular pipe is proportional to what? That is the friction factor is talking about. Friction factor in case of the, I think friction factor, you know, the Darcy's Weisbach equation, and probably I think I was having some Moody's diagram also for you. Okay, I will discuss the Moody diagram. So for option A, the friction factor, you know, the formula is what? If you solve the Darcy's Weisbach head loss, the one term was coming the what the HL is equal to or HF is equal to FLV square by 2ZD. What
Sir,
was
your
that?
cursor not seen, sir. Your cursor is not seen.
Yes.
Your cursor is not seen. Your cursor.
Oh, I have not shown the cursor, just I am telling. So just within 1 minute. Francis, you also tell your answer in the chat box whether the option A, B, C, which one is correct. Then I will discuss some concept. Okay, now I will discuss some concept. Then we'll move ahead. So probably you or think you know already the HF, the head loss in the pipe, FLV square by 2GD, diameter of pipe. for the 5. So this F, here is the question is about this F, friction factor. This F is known as the friction factor. I think you know already the friction factor is different in case of laminar and the turbulent. For laminar case, we will calculate the friction factor by 64 by Re for laminar case, and for the turbulent case, we generally follow the Moody's diagram, or the one equation is also given for this diagram called Colebrook equation. So I will discuss about later on this Colebrook equation. But for this, the friction factor is calculated by, if your flow is laminar, 64 by Re, so it is inversely proportional to the Reynolds number. So option B is correct for that. So now you question number 2. For question number 2 you go, you solve the for question number 2. In Hazen-Pawsley flow of viscous liquid, one of the following pair of the force strike a balance. In Hazen-Pawsley flow. For question number 2, the option is, first option is the inertia and viscous force. Option B is the pressure and viscous force. Option C, the gravity and viscous force. Option D, inertia and gravity force. Which one is correct? Please write your answer in the chat box. For question number 2, the Francis is telling the option A. Pradeep is telling option A. Francis, your comment I want also. The hasn't paused. Francis, you are telling the pressures and the viscous force. Okay,
Yes.
okay, okay. So the Pauli equation is this. I will write to the direct equation. So I was also put some slide about that, but okay, don't worry. The viscous liquid, the which following force is strike the balance. In the Pauli, if you see the equation for Pauli law, what is the equation for the velocity? Actually, the mass flow rate, velocity average into area of cross section. So this equation was like that, here written, pressure 1 minus pressure 2 into R square divided by 8 mu L pi r square. So this is the equation for mass flow, or you can say the m dot. This is the Pauli, the Hazen-Pauli flow equation. So in this equation, if you will see, the pressure and the viscosity term is there. So basically, the option B is correct for this question. Yeah, option B is correct for this question. Now we'll move on the next. Yes, question number 3 and 4. The flow in a pipe can be expected to be turbulent when the Reynolds number based on mean velocity. You have might have know the Reynolds number. I have discussed already. The mean velocity, I was telling the velocity whatever we use, the average velocity, that is the mean velocity. Yeah. And pipe diameter is what? Or you can write your answer in the, if option is not correct, you can write your answer in the chat box also. So you already know average by mu, or you write V average D divided by mu. So for laminar case and the turbulent case, previously I was telling the previous slide. So option C, we can go option C, but if we generally, as per the option is given A, B, C, D, it is fine. But generally for turbulent flow, the what is the actually, I think some option mistake here. If the option is like that, you go through the option number C. It is okay. But what is the actual value? If you please write in the chat box, what should be the actual value in this option? Yeah, greater than 4,000. Okay. So,
So, during calculation, do we need to, if the velocity at the end region is given, do we need to find how we will find out that mean velocity, or we take the entry velocity?
no, no, it was given. It was given in the your in question. If question is not given, some relation was about velocity and the your mean velocity and the your velocity flow velocity. So I think it's 1/5 times of your average velocity of the your five times of the velocity, your maximum velocity actually. No, I think this is wrong. For maximum, u max is equal to I think 1.5 times of the your average. So some relation was given. If question was like that, the relation was given. Yeah, already. If you not given, you just assume the whatever the velocity you write just one line. So we are assuming here the velocity is given in the question is the average velocity. Based on that, you calculate the. If the
So,
option wise, if the question like the option, then you directly solve and match your answer. Which one is correct?
so if actually if the question giving 5 meter per second at the end region, we need to calculate convert it into V average by using this 1.5 for calculating the relevance number, or we can directly take that V max.
No, no. Question was not if you are telling the question is given the at the entrance point. You are telling the like some distance. You are telling the velocity is given at that point.
Yes,
You are,
sir. Inlet point.
no, 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 no. If the velocity is given in that point, some relation was there. How you will calculate? Maybe the some in the question itself a relation was there. If not, or maybe the let's say the development length formula for if I want to write the for laminar case the 0.5 Re into depth diameter of the pipe. This is the D diameter of the pipe. So maybe if question is like that, some information was also there. Then maybe the LD was there. So based on the LD, you can calculate from the Reynolds number. You already know the Reynolds number. What is the V average into D divided by kinematic viscosity. So all the information was given. You can calculate from here the average velocity. So this type of question maybe you can expect in your exam and maybe in the gate also. This is the good question. If the entrance velocity is given or how much the average velocity or how much the average velocity and or based on the average velocity maybe some another parameters maybe need to be calculated. So you can,
So for that, we need to give. They need to give the Reynolds number, isn't it? For this case.
yeah, if the question is given like that, you are telling what you are telling, you just repeat again.
Actually, if they just give an entry velocity and then they tell us to calculate the Reynolds number, do we need to use this 1.5 and find out the V
No, no,
average?
no, just I was telling what was the your maximum velocity and the average velocity relation. One graph was there here. I think just to come off the above. Here the graph was there, na? The maximum velocity is this one and the average velocity is this one. Oh, how much the maximum velocity? V max, just for sake of your understanding, I was telling 1.5 times of the V average. Or maybe in case of the circular pipe, it may be the 2 because I didn't remember, but some relation is there. V max, let's say V max is some let's the constant K into the V average. You need to explore
For
your
that, there might be some relation, I think.
yes.
They might will give the some relation relating them, maybe.
No, actually, I'm not getting what you are telling.
Actually, maybe they will give the relation for finding out that.
Yes, yes, yes. In the question, something was there, so you will get yes. In the pipe case, it will be the two.
Sir,
I-
also if the V is given as a, in vector form or in variable form, we can calculate the V average using this equation, this integral equation.
The integration equation.
Yes, sir.
Yes,
If
yes.
the okay.
If maybe sometimes in your question was given the some variable. Let's say your velocity is given some equation format. So you will calculate the average. Some information was definitely given in your question already. So no need to worry about that. So for the maximum and the average difference is 2, not 1.5. I think 1.5 is in the case of the rectangular one. If the pipe, if the your flow is between where was this 1.5, I think when the flow is the two parallel plate. So in that case, I think your maximum velocity is the 1.5 times of the average velocity if the flow in the parallel pipe. So you need to explore your knowledge by the book. But in case of pipe, it will be the two. I am sure. So now the question number 5 and 6 is a very important question. I think question number 5 is remaining. 4 is remaining. So first we need to solve the question number 4. The stress that arises due to the fluctuation in the velocity component in the turbulent flow are the stresses that arises due to fluctuation in the velocity component in the turbulent flow. I was telling that in case of laminar flow is like that, but in case of turbulent flow, what is the velocity is like that, maybe the fluctuating kind of thing. So one average velocity is there if you calculating the average, but this fluctuation component is also there if you want to the separate the average quantity and the fluctuation quantity is there. So due to this fluctuation, let's say the u dash, so due to this u dash, which type of stresses develop in the flow, which type of stresses develop? So this is the question, very important question. So you need to write your answer in the chat box, and after 5 minutes we'll take some break of the 5 minutes. For question number 4, okay, so option number C is correct. Good. The stress, these are Reynolds stress. Let me discuss how it is. So for your just for your general knowledge, just I want to discuss some concept here about the turbulent flow. So let's say, so your in case of turbulent flow, your velocity like that, not the straight one as a. So this line represent the average thing, your complete velocity, let's say the u, and this is the fluctuation u dash. So your complete velocity, if you break down, and this breakdown was done by the Reynolds, so you complete, you can divide in two parts, u average plus u dash, that is the fluctuation component. Similarly for another direction, if you taking the 3D velocity, w also, w, that is the v fluctuates, fluctuation component, and w fluctuation component. So Reynolds, when the Navier-Stokes equation, I think you might have studied the, I think you have already done, I think, Navier-Stokes equation. So in the Navier-Stokes equation, when you averaged like that, you replace the velocity with this term, you will get this parameter minus rho u dash v dash. So this is known as the uh, Reynolds stress. And why Reynolds stress? Because the unit is like that, kg per meter cube, meter per second into meter per second. So, and the stress unit is what? Newton per meter square. You already know the pressure unit and the stress unit same. So for Newton we need the kg meter per second square. So kg meter per second square, this is represent the Newton, and this is also involved, and one m is here gone, so Newton per meter square is here. So based on this dimension, it is also satisfying the stress sum. So your fluctuation component is what given the Reynolds stress term. I think you have got some extra knowledge about that. So now we'll move on the next question, question number 5 and 6. After this, question 5 is what? The friction factor for turbulent flow. The previous question was about what the friction factor for laminar, but here the friction factor for the turbulent flow in a smooth pipe varies. The option A, inversely as the Reynolds number, directly as the Reynolds number, as a square of the Reynolds number, or inversely as a 1/4 power of the Reynolds number. So this is the question. So please write your answer in the chat box.
So it's actually for the laminar flow, the ensemble will be inversely. Uh,
Yes. For
uh,
laminar flow, your friction factor was about 64 by Re. What you are telling?
okay, sir.
Yes. So basically, these are the info 64 by Re and whatever. And the one equation for the turbulent flow is also given. So this is a very useful. We need to remember.
So actually, the friction factor is considered for the friction between the fluid and the pipe, isn't it? And then
Yes,
what
yes,
is when you
yes,
saying
yes,
smooth pipe?
yes.
Then why we are saying it's a smooth pipe? If it is a smooth pipe, then there won't be any frictions in it.
No, no. You are telling the if pipe is smooth, then the friction between the fluid and the wall will be the zero. You are telling like that.
Yes, sir. Is it like that?
Yeah, no, no, no. It is not the actually the smooth is written, but some friction was there. So that's why that is why here the question is like that. If the friction factor for the turbulent flow in a smooth pipe. Smooth pipe means the newly pipe, not the smooth means you not think like that. Let's say because of the question whatever the Colebrook equation was given, he was clearly written. This equation is give the answer whatever is giving. It is for the smooth pipe means the newly pipe, not the 2 or 3 year. You are if you are going to calculate the pipe, uh, pipe is uses already usable this. So here is the meaning is smooth is this. You are not use this equation, that is the Colebrook equation for the use use already uses pipe. So it smooth means this.
Okay, sir.
Yes. The final equation I have written, I will write here. Some famous researcher was also in fluid mechanics, very very especially in the turbulent flow. The Nikuratse and the Prandtl and the Von Karma. He has and they put a lot of effort in the turbulent flow. So you always remember the Nikuratse. These researcher will all use frequently in case of the turbulent flow. These researcher findings actually we will use several times. So Pradeep is telling for question number 5 option D. Okay. So the equation is for, okay, I think we'll see the first equation. For the turbulent case, friction factor you will calculate like that: 2.0 log epsilon by d divided by 3.7 plus 2.51 divided by re root f. So this is the equation given by the Colebrook. PR. This equation is given by Colebrook in 1993, in 1939 actually.
So what's the term written after the RE? RE root of, is it F?
Yes, yes. This is written. This thing is written re root f.
We have 2F in the LHS and RHS.
So this is the equation given by the Colebrook for finding the your friction factor, that is the F, in case of the turbulent flow. But the this is a very implicit kind of thing. Implicit means what? Whatever we are going to find out, this side is also given, right hand side, and the, that is the left hand side, and the right hand side is also given. So this is the very implicit. But if somewhere the implicit this things is happening, this type of equation we generally know the implicit kind of equation. So this type of equation we generally follow the iteration, that is a put some value and get the answer. So this is a, but here the question is the friction factor of the turbulent flow in the smooth pipe varies. So how it is varies? So when you will solve this question, you will be get your friction factor is varying with the inversely of the 1 by 4th power of the Reynolds number. Actually, I have find out. I was trying to find out the answer of this. How is 1 by 4th of the power of the Reynolds number is varying? But actually, I didn't get the concrete result. But in the previous year question of the NPTEL, this option is correct. The 1 by 4th of the, yes. So I was, so for the question number 5, you meantime you need to remember the inversely as a 1 by 4th of power of the Reynolds number. Your friction factor, I think it will be, if you solve this question is like that, let's try to solve. uh, if you will free the here root f, what will be the happen? The minus 2.0 and log and some, let's say the equation is e by d 3.5 plus 2.5 by re root f, and square is here because 1 by root square is there. And if you will calculate the f, what will happen? This is the, actually minus 2, it will be the minus 2.0 log e by, I think some this whatever the root f is written, if we do the mathematics, lots of mathematics for solving this, you will be get the your friction factor is inversely proportional to the 1 by power of the Reynolds number, that is the 1 by 4. But for this, your Reynolds number is, if you will see, the your Reynolds number is already, and I think this root you will be removed from here. I think it will be the 1 by 4 power will be definitely you will get. But uh, from this equation you will be get the 1 by 4 power. So the question number 6 is what? The question number 6, the eddy viscosity means that is what? It is a physical property of the fluid, eddy viscosity. Same as the kinematic viscosity, always associated with the laminar flow, and apparent viscosity due to the turbulent flow. So this is the question 6. So you need to write your answer in the chat box. Yes, definitely. I will take some few minute breaks after that.
Thank you, sir. Maximum
Yes,
come,
yes.
sir.
Yes, yes. You will come. We'll meet again. The 1906 time is there, but we'll meet on the 1910.
Okay, thank you, sir.
Yes. So now we'll start again. Yes, question number 4 6, the option D is correct. The eddy's viscosity means, but now I want to give some. Pradeep, you are there? You are here? Francis, you are here?
Yes, sir.
Okay, I think Pradeep is not. Let's wait 1 or 2 minutes. Then I will give some concept eddy viscosity. Actually, the in case of the turbulent flow, the how we will calculate the shear stress. Actually, the concept behind. Pradeep. So the basically I will solve the next question. Then we'll. Question number 7 is about which of the following represent the major energy loss: bend, pipe fitting, sudden expansion, or the friction loss. So please write your answer in the chat box. Which option is correct? Yes, for question number 7, the option D is correct. Because the bend in pipe, that is the L section, or maybe the another section also, another type also, and the pipe fittings and the sudden expansion and sudden contraction, these are come under the minor losses, but the friction loss is very much. Question number 8 you can also solve, Francis. The hydraulic gradient line is the sum of pressure head, datum head, and the kinematic head. I think we have discussed lots of on that line, energy gradient line and the hydraulic gradient line. Here the question is about the hydraulic gradient line. So hydraulic gradient line, what is represent? Question number 8. Yeah, it is the false. Hydraulic gradient line basically represent. Pradeep, you are here? I think he is in the maybe the network issue or some another issue. So Francis, basically the hydraulic gradient line you represent, energy gradient line represent the all, the pressure head, datum head, and the kinetic head. You already know the energy equation, the Bernoulli equation, P by rho z plus V square by 2z plus datum head. So this is the constant. So this represent the pressure, this is represent the kinetic, and this represent the datum head. So this is all the energy is represented by the energy gradient line, not the hydraulic gradient line. Energy gradient line. But the here question is about the hydraulic gradient. So hydraulic gradient line basically represent what? Hydraulic gradient line represent your datum, that is jet, and the pressure. This type of concept, if you will aware about the fluid mechanics, then your soil mechan if you are the mechanical engineer, I don't know much about the what is the your cascading, that is your fourth, fifth, sixth semester of syllabus. But in case of the civil engineering, in soil mechanics, this concept is used. Every let's say if you learn the fluid mechanics, then lots of your concept is clear in the coming semesters. So it is very important to uh, learn the basics of fluid mechanics. So
I have a question related to this. It was in an exam. The question is actually, if an energy gradient and hydraulic gradient lines are drawn for a flow through an inclined pipeline,
yes.
uh, they have given the four values like static head, friction head, datum head, and velocity head. They are asking for the starting from the arbitrary datum line. Above types of head will be in sequence. These four thing will be in which sequence we will be seeing it.
Oh,
Static head, friction head, datum head, velocity head.
friction head, datum head, and
Static head, friction head, datum head, velocity head.
in question is asking.
Yes, they are asking starting from the arbitrary datum line, the above types of heads will be in this sequence, and they are giving some sequence.
Okay. No. Basically, actually, you in case datum you will select anywhere. If let's say the for example, this is a pipe flow case. Let's say the pipe is flowing like that, or maybe the downfall here. So your datum you can select here also. Arbitrary means you can select here also, or you can select in the mid also. But you need to remember when you will go, your assumption should be similar everywhere, positive. When you will come the down, your this is the value will be negative. You can change interchange, or you can use the interchange also. If you take the negative this thing, you need to take the below one is the positive. If you are taking here, so this is the meaning of the arbitrary datum head. And after that, what was your question?
They are asking starting from the arbitrary datum line, the
Yeah.
above types of head will be in sequence.
Yes.
And the heads are given static head, friction head, datum head, and velocity head.
Okay. Static, datum, kinetic, and that is the velocity and the pressure head. And what they asking actually?
They are asking for the sequence. I mean, 3, 1, 4, 2. First one is
Okay.
static.
Now I'm getting. Okay, which one you will be get first, right? This is the question. If you are taking the arbitrary datum, which energy you will get first, and after that which energy, after that which energy. This is like that.
Yes, sir. Yes.
Okay. So question should be actually I'm not getting the correct question, because this type of question, how we can tell the which of which phrase which actually energy will get first.
Actually, they have given the answer. I mean, the response sheet was actually given. Like they in the option that they have given is actually datum head is given first, then
Definitely, if you are going to measure from datum, the first is the datum. Okay, second one.
then the second option is static head.
Okay, and third one.
uh, Third one is velocity head, and the final is friction head. But I
Okay.
was actually confused with that the theory that I have gone through. Actually, the energy line should be the top, and the energy line is associated with this velocity head also, isn't it? So,
Yes, yes.
but this is actually the response sheet that they have given. Actually, it was actually a competitive examination.
Actually, I'm not getting. If you are going to measure something, if pipe is like flowing, then if your pipe is flowing, your pressure head and the velocity head, if you are going to measure by some instrument, your pressure head and your velocity head will be the measure same. If you are going to measure somewhere, though, your at same time you will get the both energy, pressure as well as your velocity both. But I think question is framed, I think in a different way. So if I will see the question, then I can some give the comment you another. There is no meaning of my comment on this.
So I will mail that question.
Okay, you will mail me, then I will tell definitely. I will
Okay.
see once I will get the answer, then I will definitely discuss to you. So I want to tell something, the eddy viscosity. Pradeep, I think I don't know coming here or not. Pradeep, you are here.
I'm back, sir.
Okay, okay. So the question number 6, you are, if you have, okay, okay, no problem. If you have the question numbers, you see the question number 6, the eddy viscosity means is that it is the
D, sir.
viscosity, yeah, it is the viscosity which is actually developed by the turbulent flow. So option D is correct for question number 6, but I need to give some more clarification on that. So actually, if the flow, what if turbulent flow is like that, turbulent flow. So basically, in case of turbulent flow, if you need to write the your shear stress, that is the in laminar case we have already seen the Newton's law of viscosity, du by Ly. So this is the stress. But in case of turbulent flow, if the flow is turbulent, so Vt and du by dy. This is what, this mu is the your fluid property, and this is due to the your flow. So you need to always remember this is a fluid property. For, I think, for water it is different, for oil it is different mu, but mu t is depend on the flow property. So this is the basic difference. So your total stress may be the combined of both mu du by dt plus mu t du by dy, not t, here the y is all. So your combined stress is like that, mu plus mu t du by du. Somewhere you have also seen in the case of the turbulent flow how to calculate the shear stress. So this is the formula, and another formula also there, but just for sake of understanding the difference between the dynamic viscosity and the eddy viscosity, the basic difference is that eddy viscosity is the flow property, it is developed by the flow. So question number 7 was about the which of the following represent the major losses. You all know the bend in the pipe, fitting in the pipe, and the sudden expansion and the contraction are the minor loss, and the friction loss is the major loss in the case of pipe. And the question number 8, I think You already know, you both. The hydraulic gradient line represent what? The datum head and the pressure head. Energy gradient line represent the pressure head, velocity kinematic head and the datum head. So this question number 8, option B is correct. That is the false. The hydraulic gradient not represent the pressure head, datum head and the kinetic head. So the question number 9 is, which of the following represent the losses of head at the exit of the pipe? If there is a pipe is there, the water is flowing, so at that point which type of losses is happening? So the formula basically is asking, these are the derived formulas. So I need to discuss some Moody's diagram also for you. It is a very important thing, because all these things every time people discussing, but Moody's diagram sometimes and the development length sometimes in the classes not more much discuss as the frequently discuss the all other things. So this is a very important thing I want to discuss, but in the meantime I need to see something for you. Okay, for yeah, somewhere the option B is correct, the v square by 2g if the exit kind of thing. But on that question I want to give some clarification. So basically head loss is represented by, okay, so your head loss actually represent by both. Let's say the HL is the head loss in the pipe, so H major and H minor. So major you have already seen, the it is due to the actually pipe friction, but the minor losses lots of things is there, like bend, exit, inlet, and the another thing also. But some formula is there for the major loss. You write already v square bit. This is the average. You already remember 2ZD plus for that v square by 2G. K is a factor. It's depend on the which type of it is vent, or for vent it is different K, for exit it is different, for inlet it is different. So lots of K is there for different cases. So basically I have, actually I want to put for exit actually it is equal to the 1, K is equal to, and for inlet it will be the different, for this is different. So you need to go through the book, you will definitely get the K values. So basic idea is that your friction losses by both major and the minor. So generally we ignore the minor losses. We concentrate on the major losses, that is the friction loss. Now we coming on the question number 10. For
So is the K actually the CD coefficient of discharge or anything like that?
no, K is depend on, K is calculated based on the experiment, how much it is given. K is maybe the sometimes for the some case 1, sometimes the 0 0.3, 0 0.5. So it is different. In the book lots of K value is there.
Is there any name for it, like sensitivity factor or like there
Actually,
is a notch sensitivity factor, isn't it? Like that.
what you are telling, Francis, you tell again.
Actually, we name some constant term, isn't it? Like notch sensitivity factor, coefficient of discharge, like that. Is
Yes,
there any name for that? K.
yes. It is like that. It is like that. This constant we will multiply. If let's say I have some example for pipe exit, this K is for pipe exit. If the flow is your that is a K is equal to alpha. You already know alpha is what, the kinematic energy correction. You already know the kinetic energy correction. Kinetic energy correction for the pipe exit, it is equal to, if the flow is laminar, fully developed laminar, it will be the 2. In case of turbulent flow it will be 1. So this question, if you will see, uh, if the flow is laminar in this question, then for the exact value will be the 2 by v square by 2g. But in the question is not given whether the flow is, and if the flow is turbulent, then 1 into v square by 2g. But in the question not given anything. With this option, if we see the option in actually cannot say, means here meaning is that we cannot calculate, but we can calculate. So if we see the three option, there is in 2 is nowhere. So we just generally assume the flow is turbulent, and the option number B is correct for this question. If the
So
your,
for the value is 1 or 2.
yes,
For the turbulent value is 1 or 2.
yes. If the laminar case, the value will be the 2.
So
Actually, K is representing here the correction thing, how much your velocity will be the disturbed due to this sudden increase, sudden decrease, bend, and all these things. Yes, please ask.
actually the value should be higher for the turbulent, isn't it? Since the more loss will be getting for the turbulent.
No, but as per the calculation we have seen, the yes, if you are thinking like that, not this is not case. But for if you go for the mathematical solutions, you will see the kinetic, that is your k value is 1 for the turbulent flow, and your actually for exit, this is not for all. That is the this is you not think the flow in the pipe, you just think at the exit location. Exit means is that this is not diagram for exit, this is the diagram for exit. Let's say the one reservoir is there and the water is entering in this reservoir. So at that location what will be the effect, how much energy losses at that location, not everywhere. So if the flow is laminar, it will be the 2 times of the 2z, and if the flow is turbulent, it is already fully developed. You always remember, after getting this fully developed concept, you always remember, if anywhere people is talking, not telling the we are assume the fully developed, you already remember the whatever we are discussing in the range of the in the range of the fully developed, not before the fully developed. Whatever is question is framed, it is before the fully developed, and not before the after the fully developed length. So here the fully developed turbulent flow, it will be the 1 v square by 2. So now the question number
So
11.
actually,
Question number
what is the significance of that fully developed region? Is there any practical application for that fully developed region?
yes. Because in the
Nation.
fully developed region, what I was telling, it was your core zone is like that. But in fully developed region, your velocity diagram is similar throughout the channel. So if you will calculate the velocity, because you know the your shear stress and the everything pressure is related with the velocity. So we always focus on the velocity, velocity finding in the what fluid flow. So if you will calculate this velocity, this is the higher velocity is achieving by your fluid. So based on that, you will be the design everything. Either for the first before the development length, what is your velocity is not achieving at the maximum. So this is the reason we calculate the everything after that. So system will be the stable, right? Based on that, we will assume further design and everything. So this is the reason. So question
So
number,
the stress of everything will be lower at that region, or
yes,
stress will be higher at that region. I mean, if we are designing a pipe, do we need to design it more strength for the in inner region?
yes, because if you will calculate this velocity, let's say if you are calculating the velocity before the development length, your velocity will be the less as compared to the maximum whatever you are getting in this zone after the development length. So if you will design under, let's say you are calculating the shear stress, how much the shear stress, and you are taking the less velocity for calculating the shear stress, what will be effect when the maximum velocity is come, then your pipe will be the brushed or something will be affect whatever, if you be designed like that. So we need to always calculate velocity, the how much the maximum velocity in the pipe, based on that we will design. Maximum, it means that you already know the maximum is related with the 2 times of the average. So if you want to design the average, if you are getting the maximum velocity, divide by 2 and you will get the average kind of thing. So here the main reason is that the main utilization of the fully development length is that we need to calculate the actual velocity what is happening inside the pipe or duct, and also in the open channel flow. So
So
this is
if you
the
take the
basic.
outside velocity, then it will be like a overestimation.
Oh, no, 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 no. Yes, yes. We are actually, if you are looking for any design, what we are doing, we are taking the factor of safety. We are looking the factor of safety. What? Because the lots of assumption we have taken in the design before the mathematical. Let's say the water is flowing, and we are going to write the is flowing water in terms of the mathematics. So we have considered the lots of assumption. For fulfilling the assumption, we have take the in the not case of the only fluid mechanics, in the other subject also we have take the factor of safety. Why? Because of we assume before derivation of anything as per the writing the mathematics in the mathematics equation assumption. So fulfilling the assumption, we take the factor of safety is somewhere the 15% more, somewhere the 80% more, somewhere the 50% more. So based on the sensitivity, how the system is sensitive, based on that we take the factor of safety. Here is also the case. We are if we design in the this velocity before the development length velocity, what will be the happen? Your maybe the chance of the failure of your system. So we never design on that. So this is the case. Or you are telling the over, this is not over. Why? Because after the certain length, the velocity is flowing, is the your whatever after the development length is flowing, is the similar flowing is like that. So for a small length, for a small length only uh, your less velocity is in the system. So what we are as an engineer, we focus save the all in entire system, not only a small system. If you are going to design something like the under velocity, then this system will be your stable, but this is not it may be the fail. So we are looking, because this is a long pipe, and for more stable, for all system stable, we need to consider the maximum one. So I think, Francis, you got the reason behind it.
Yes, sir.
Okay, so the question number 10, if you see the question number 10, for a study in compressible flow through a closed conduit of uniform cross section is there, the direction of flow will always be from higher to lower elevation, from higher to pressure, and we just see the option number C, from higher to lower velocity, from higher to lower piezometric head. So please write your answer in the chat box for this question. Okay, for question number 10, Pradeep is already written. For a steady incompressible flow, incompressible, you all know the density is not varying, closed conduit of uniform cross section, somewhere the piezometric cross section also there, prismatic, actually prismatic. Sometimes the uniform uh, term is written by the prismatic, so you always don't confuse with that. The uniform cross section, the direction of flow will always be from higher to lower elevation, from higher to lower pressure, from higher to lower velocity, from higher to lower piezometric head. So basically in the piezometric head you have seen the all your pressure head and your datum head is considered. Pressure head and datum head both are considered in the piezometric head. So best option is what? Please, Francis, you also give your answer in the chat box. What is your view on that? Yeah, option D is correct. Okay, fine. Now we'll move on to another question. Yes, please. This is a very easy question.
So, what was the problem with that pressure term?
No, here is the pressure. Only pressure means is that if you solve the energy equation, what you will get the pressure and your datum also. If your pipe is like that, let's say this is like that, your pipe. What will be the happen? Maybe the your datum height. If you will solve the this is and this is. So only you not see the pressure, you will see the pressure as well as the piezometric head, as well as the datum head. Only in this type of flow, only the pressure is not responsible for the flow. Your energy basically you're responsible for flow. The higher energy to lower energy for
Okay, sir.
such type of yes. So piezometric head means is what? The pressure is also included in this, but we are choosing the most appropriate thing. So piezometric is correct. If we see the now the question number 11, find the Darcy's head loss due to the friction of pipe diameter this and length is this much, and through which water is flowing at the velocity 3 meter per second, and velocity is given the 3 meter per second. You always considered in this question is not given the after the fully development and the average velocity. You always consider this 3 meter per second is the average velocity in the pipe, and this velocity is given after the fully development, and take the friction factor is 0.01 024. So based on that, you calculate the answer and tell how much. Before this question, I have one theoretical question. You just see. First, you need to solve this 11 number. So you all know the actually the Darcy's head loss HL is equal to FL V square by 2GD. So you need to put and tell the answer how much you are getting. For question number 11, length is 50 meter and the V is the 3 square divided by 2 into 9.81 into D is 0.3 0 point. Yes. So please write your answer in the chat box how much you are getting and which option is correct. You can also write. Yeah. For question number 11, the option A is correct. The 0.78. Francis, your answer is similar kind of thing. If not matching your answer, you just check your calculation. Here the your diameter is given in the mm, you need to convert in the meter or 0.3 meter and everything in the meter, so we will get the answer 0.7828. So question number 12 you can also attempt. A 2 kilometer long pipe of 0.2 meter diameter connect two reservoirs. The distance between the water level in the reservoir 8 meters. Okay. The Darcy's friction factor of the pipe is 0.04. Accounting for friction, entry and exit losses, the velocity in the pipe is what? So this type of question is very important for your GATE exam also. For question number 12. So before discussing the question number 12, you just see the question number 14. This is a very direct answer is that you need to always remember. Maybe this type of question you may be the face in the exam and also the some competitive exam also. So for question number 14, what is the head loss coefficient in sudden expansion shown in the shown in the figure below is proportional to. So actually this is the case of the sudden expansion. The pipe is sudden expand from small d to capital D. So your the is proportional to what? You always head loss, you know, the k v square by 2g. So it is asking the what is the value of k. So the k is your 1 minus a small d square by capital D square whole square. So this is the uh, basically your head loss formula, 1 minus d square by capital D square v square by 2g. So with this you will be calculate your. So now we'll move on the question number 12. Your question number is 12 is telling 2 meter long pipe of the diameter connected to reservoir. Okay, one reservoir is there and the another reservoir is there. And the connected, let's say This is the pipe is connected from here to here. This is the diameter of the pipe is 2 meter and the length is 2 km. This is the entry and this one is the exit. So at the exit your loss HL is equal to how much? V square by 2G, and at the entry V square is some 0.5 V square by 2G. At the entrance you will be sometimes the yes 0.5 you will take. So what is, and the difference between the water level in the reservoir is 8 meter. Let's say the water level in this reservoir is full and here is the water level in this much. So if you take the difference, how much? 8 meter. And Darcy's Weisbach friction is there. If the Darcy's Weisbach friction is there, you will calculate easily velocity, average velocity. How much is given? 0.404 equal to F. Actually, we need to not like that. Okay, Darcy's friction factor of the pipe is this. So for that you will apply the Bernoulli equation, you already know. Or if you will calculate the HF, how much? F L V square by 2ZD. Here F is given, L is given, V is not given, D is given. So V is not given, so you cannot calculate this HF. So what you will do? You apply the Bernoulli's equation. How will, at that and at that you write the Bernoulli equation. Let's say that consider the datum is this. Datum you need to take this one datum also, no problem. This is the datum. So you need to write the Bernoulli equation. So P1 by rho z, if see atmospheric pressure, so it will be the 0. That is the V square by 2G. Or you can take the okay the V square by 2Z, and you take the Z1 plus in the another case V2 square by 2Z. Here you can take the V1 plus Z is how much? Here the Z is not, because at that if you go the at that point your H was 8, that is your Z1 is equal to 8, but your water level is this much, so here the datum is this much, so it is 0. And your all losses means you have 3 losses. HL all, here I have written HL all means this HF and plus H entry plus H exit. HF FL V square by 2GD in the pipe, this is talking, and now 0.5 if you talking about the entry V square by 2G and exit is how much? V square by 2g. So this is the head loss equation, and so Z1 is given your, so I think based on that your velocity in this reservoir and in this reservoir will be the 0. So only Z1 is here. So 8 is equal to what? 8 is equal to your all losses. In the all losses, you know the everything. FL V square by 2GD plus 0.5 V square by 2G plus V square by 2G. Only V is unknown. So you can easily calculate how much V will be come out. So please you try to
So
yes.
actually, do we need to take the difference from the first reservoir level to second reservoir level? Actually, the pipe is placed in some height, isn't it? So, should be taking the difference of the surface level to the pipe level when the both the level is equal. I mean, the reservoir will be balanced when it is in the same level, isn't it? Pipe level,
No, no,
isn't it?
yeah. You are telling just for qualitatively, I have just to mention here the difference is 8 like that. But you know, the water level is come actually the difference is that you are asking is what if the water level is this much is coming in this reservoir also. So this is your question. What is your
Actually,
question exact?
if the both the level is same, there won't be any water flow, isn't it?
No, not flow. If the level is same in the both, but here is what the water level is. Your the difference is given actually.
What made I say? Actually, the pipe is placed above the level of that second reservoir, isn't it? So, when we compare the first reservoir's surface level and pipe level, should we take the difference from the
Yes, basically what I have drawn here. One reservoir is given but with the full water level, right? And one pipe is connected in the second reservoir, and water is flowing, and at some water is flowing is in this water already is coming. But at a particular instant of time, what I have observed is the difference in the both water level in the first reservoir and the second reservoir is 8 meter. So for that particular observation, I want to calculate the velocity in the pipeline, what how much. So this is the idea. This is in the actual case what you are telling. If the water level will initially
so
water
I
level
got
is
this.
not that much. Water level was somewhat I was observing at a particular time. Water level was this much. So for that particular time, how much the velocity in this pipe. So this
So
is the
can you explain it again? And my network just was.
okay. No problem. In the we have only two reservoir is given here, and at a particular time I have observed is what in the first reservoir water was full, and the second reservoir is water is that at a, but after some time when the water is flowing from this pipe, the reservoir is moving up to that the level in the second reservoir the add to that much, and for that particular time the difference between the water level reservoir 1 and water level reservoir 2 is 8. So for that particular time, I want to calculate the velocity in this pipe, how much. So based on that, you can calculate. So F is already 0.04 H, and L is already 2 kilometer. You need to put in the meter. If you put all the data, you will get the velocity.
So,
Now,
for that case, we need to place the pipe at the second reservoir level, isn't it?
yes,
If we calculate like taking the surface level of both reservoir, then the velocity will be like pipe will, we need to place that pipe at the level of the second reservoir, isn't it?
No, actually, I'm not getting your answer. What you are asking? Question. Please write again. Ask your question.
So if we take the head difference as first reservoir and the second reservoir,
Yes.
then it will be like the water is flowing from the first reservoir to the
Second
level
reservoir.
of second reservoir, but the
Yes.
pipe is actually placed if 1 meter above the second reservoir level, then the velocity calculator will be different. Velocity available at the pipe will be different, isn't it, from the with reference to the first reservoir?
No, no. You are in
It's
the
not
in.
actually the horizontal. If it's inclined, then it's okay. If it is placed in horizontal level, the pipe is placed in the horizontal. Then I mean the head difference will be different, isn't it? The velocity of the pipe.
Actually, you are asking is what your pipe orientation you are asking about or what?
Uh,
No, no.
I mean,
Some slope is there. Some slope is here in the pipe. Reservoir one and reservoir two. Some slope is there with the slope with the gravity. Water is flowing in the reservoir one to reservoir two. On anyway, the height is there in the your level. In the reservoir first, your water level is much as compared to the water level 2 in the reservoir 2, so definitely water will flow like that. And at a particular time we have observed, and one guy observed the difference was the both reservoir is 8 meter. So at that particular time how much the velocity in the pipe based on some data is given, we can, you will just tell the answer. So this is the given question, so we are trying to solve how much the velocity in the pipe. So your, I think, question is about the, if the pipe is horizontal, then pipe, if the horizontal is what means your water level is this much high in this.
sir, I think I will mail it along with the this stuff. I think if I write it, maybe it will be more understanding.
Yes.
Okay.
Okay, so for that you need to calculate if the velocity. So f you will put here 0.04, and L is given 2 meter, 2 kilometer actually, and velocity is unknown, and just I want to try to calculate 9.81. D is given 0.2 plus 0.5 into, that is your V square, plus V square.
Sorry, A. A is coming.
Yes, so 0. Yes, so option number A is correct for that. So based on that concept, you will be, you can expect the question in your final exam and as well as gate exam and another competition exam also. So just for today, that is enough. So we'll meet again on the next class, the next Monday, coming Monday. This is the 8th week, and the fluid mechanics course is a 12-week course. So in the final, after the 12 week completed, I will take one summary classes. In the summary classes, we will basically revise the basic concept of the fluid mechanics and some problem also. Yeah, that class I think was 1 hour or maybe the 2 hour also, but not more than 2 hour. Maybe the some 1 hour and 1.5 hours. Last class. But coming 4 classes will be the 2 hours. The Monday, so you will get the notification by the mail. So thank you all.
So, can
Okay.
you once again share your mail ID?
Mail ID, yes, I can share you. So I think you will get. You got?
Yes, sir.
Okay. Okay, thank you. We'll meet again on the next classes.
Thank you, sir.
Okay, thank you. Bye bye.